Right now, close your mouth. Pick any note at all, and hold it for 10 seconds. Feel where the vibration goes, not in your throat. Higher, behind your eyes, behind your cheekbones, somewhere in the back of your skull that you cannot precisely locate. You did not put the vibration there deliberately. Your anatomy did. And what that anatomy is doing in those 10 seconds, through mechanisms that took scientists decades to even begin mapping, is the subject of everything that follows. Humming is one of the most physiologically active things a human being can do while sitting perfectly still. That is not a poetic statement. It is a measurement result, and the gap between what most people assume is happening when they hum, not much, and what is actually happening at the molecular level inside the cavities of your face, your brainstem, and the electrical rhythm of your heart, is one of the stranger stories in modern physiology. There are 5 distinct mechanisms. They operate in parallel. Each is independent enough to stand alone as a significant physiological intervention. And they are all triggered by the same action: closing your mouth, producing a tone, and sustaining it. The first mechanism lives inside your sinuses. Your sinuses are not simply empty chambers. They are lined with a specialized epithelium that continuously produces a molecule called nitric oxide, NO, a colorless gas with extraordinary biological activity. During normal nasal breathing, some of that nitric oxide makes its way into inhaled airflow and is carried into the lungs, where it acts as a vasodilator, relaxing smooth muscle in pulmonary blood vessels and improving the efficiency of oxygen exchange at the alveolar level. This is one of the primary reasons the nose outperforms the mouth in respiratory function. Mouth breathing bypasses this delivery system entirely. The lungs receive none of the NO priming that nasal breathing continuously provides. This is not a small difference. It is a fundamental shift in pulmonary gas exchange efficiency that persists with every breath. In 1999, Eddie Weitzberg and John Lundberg at the Karolinska Institute in Stockholm published a paper in the American Journal of Respiratory and Critical Care Medicine that changed how researchers thought about humming. They fitted subjects with sampling catheters in the nasal passages and measured nitric oxide output during quiet nasal breathing, then during sustained humming at the same respiratory rate. The difference was not modest. During humming, nasal nitric oxide concentration increased by a factor of 15. Not 15%. 15 times. The vibration of humming acts on the sinus walls in a way that quiet breathing does not. It appears to physically agitate the airway epithelium, triggering a surge in nitric oxide synthase activity, the enzyme that catalyzes no production from the amino acid L-arginine. The reason matters as much as the number. Nitric oxide is a signaling molecule with a half-life measured in seconds. It does not accumulate. Each surge is real-time, local, and functional. In the lungs, elevated NO concentrations relax bronchial smooth muscle. The identical mechanism, incidentally, that sildenafil exploits pharmacologically by inhibiting the phosphodiesterase enzyme that breaks NO down, allowing the vasodilatory signal to persist. In the sinuses themselves, NO is a potent antifungal and antimicrobial agent. Concentrations as low as 200 parts per billion are lethal to multiple respiratory pathogens, including influenza A. The paranasal sinuses are anatomically prone to stagnation. Their drainage orifices are positioned poorly relative to gravity, and in the absence of active ventilation, they become a warm, moist, effectively closed environment. The vibration from humming generates oscillating airflow through these drainage channels, exchanging stagnant gas for freshly produced NO-rich air from the sinus cavity. Weitzberg and Lundberg measured the exchange rate and found that humming increases sinus ventilation, by a factor of approximately 98 compared to silent expiration through the nose. One note: 15 times the nitric oxide, 98 times the sinus ventilation. The clinical relevance of this is not purely theoretical. Post-COVID research has identified sinus stagnation and impaired mucociliary clearance as factors in prolonged upper respiratory symptoms. Weitzberg and Lundberg's data suggests that the mechanical oscillation created by humming may partially substitute for the airflow dynamics that normal mucociliary function provides, not by replacing the cilia, but by physically moving gas through channels that cilia alone cannot adequately ventilate. The physics of the mechanism does not require large clinical samples to validate. Oscillating airflow exchanges gas. That is not a hypothesis. It is fluid dynamics applied to anatomical geometry. But there is a second mechanism operating through the same vibration, targeting a completely different system. The vagus nerve is the longest cranial nerve in the human body. It exits the brainstem at the medulla oblongata, travels down through the neck alongside the carotid artery, branches into the chest to innervate the heart, lungs, and esophagus, continues into the abdomen, and makes contact with nearly every major organ in the torso. It is the primary conduit of the parasympathetic nervous system. 90% of the fibers in the vagus nerve are afferent. They carry signals from the body upward to the brain, not from the brain downward. The vagus is primarily a sensory organ reporting on the state of the body, and the implications of that directionality are profound. When the vagus signals the brain that everything below is functioning well, that inflammatory markers are low, that heart rate is steady, that gut motility is smooth, the brain's threat detection circuitry quiets in response to the incoming report. The body does not wait for the brain to decide to relax. It sends the memo upward, and the brain follows. Kevin Tracy at the Feinstein Institute for Medical Research mapped what he called the inflammatory reflex, a vagally mediated circuit in which acetylcholine released by vagal terminals in the spleen suppresses macrophage production of tumor necrosis factor, TNF-alpha, a primary mediator of systemic inflammation. This circuit means that vagal tone is not simply a stress response measurement. It is an immune regulatory variable. Low vagal tone allows inflammatory cytokines to circulate unchecked. Higher vagal tone actively suppresses them. The same nerve that slows your heart rate and relaxes your intestines is also serving as a real-time immune modulator. Tracy's work, published in Nature in 2002, showed that electrical vagal stimulation in animals reduced systemic TNF-alpha levels by as much as 75% within 20 minutes of stimulation onset. A 2016 clinical trial by Koopman and colleagues at the Academic Medical Center in Amsterdam extended this to humans. Implantable vagal stimulators reduced inflammatory biomarkers and joint damage scores in patients with rheumatoid arthritis who had failed standard pharmaceutical treatment. The vagus is a direct biological lever on systemic inflammation, not a metaphorical one. What most people do not know is that the vagus nerve has a branch that surfaces on the skin of the outer ear. This branch, called the auricular branch of the vagus or Arnold's nerve, provides sensory innervation to the conchal bowl, the hollow curved depression at the entrance to the ear canal. When this region is stimulated, signals travel up the auricular branch, enter the brainstem, and have measurable effects on vagal tone throughout the body. Transcutaneous auricular vagus nerve stimulation is currently being studied clinically for treatment-resistant depression, epilepsy, and inflammatory conditions. The Freiburg team under Rainer Serber published stimulation protocols in 2019, showing measurable reductions in heart rate and increases in heart rate variability following auricular vagus stimulation. The same physiological signature that indicates increased parasympathetic activity. Humming produces sustained vibration in the soft tissues and bony structures of the skull that propagates throughout the cranial vault. The vibration reaches the auricular region through bone conduction, producing a low-level oscillating mechanical stimulus on precisely the surface that Arnold's nerve innervates. This pathway has not been studied with the same rigor as direct auricular electrical stimulation. And the honest characterization is that the anatomical connection is solid, while the functional evidence remains preliminary. But what has been measured is this. People who hum regularly show elevated vagal tone on resting HRV measures, and brief humming sessions produce acute heart rate reductions consistent with parasympathetic activation. The mechanism is anatomically plausible. The effect has been measured. The direct causal link through the auricular vagal pathway specifically is the piece still being assembled. Now I want you to think about heart rate variability for a moment, because this is where the third mechanism enters, and where the physics becomes unexpectedly precise. Heart rate variability is the variation in time between consecutive heartbeats. A healthy heart in a resting adult does not beat with the mechanical regularity of a metronome. It accelerates slightly on inhalation and slows slightly on exhalation, a pattern called respiratory sinus arrhythmia, driven by the rhythmic modulation of vagal output by the respiratory centers in the brainstem. High HRV, larger fluctuations, is consistently associated in the literature with better cardiovascular health, better emotional regulation, better cognitive flexibility, and greater resistance to physiological stress. Low HRV is associated with depression, anxiety, cardiovascular disease, and all-cause mortality. Emergency medicine physicians now use resting HRV as a predictor of sepsis outcomes. Psychiatrists use it to track recovery from major depressive disorder. It is not a perfect biomarker, but it is one of the most robustly replicated windows into the functional state of the autonomic nervous system. Chanting and humming are among the most potent known methods for acutely increasing HRV. A 2016 study by Bernardi and colleagues found that chanting a yogic mantra at its natural pace produced approximately 6 respiratory cycles per minute. The specific respiratory frequency at which baroreflex sensitivity is maximized and HRV peaks. At 6 breaths per minute, the oscillations of the respiratory cycle, the heart rate cycle, and the arterial pressure wave produced by the baroreflex fall into a coherent resonance, amplifying each other in a feedback loop that researchers call cardiovascular coherence. Humming at a sustained tone constrains respiratory rate automatically. You cannot hum and breathe simultaneously. The exhalation becomes the hum, prolonged, controlled, and metronomic. The inhalation follows. The cycle drifts toward 6 breaths per minute without deliberate effort, and the heart follows the rhythm into coherence. The resonance is not a metaphor. It is a measurable state characterized by synchronized oscillations of heart period, blood pressure, and respiratory volume at approximately 0.1 hertz, a state that no pharmaceutical agent currently on the market replicates with equivalent fidelity. And here is where the story changes. Because beneath the cardiac and respiratory effects, there is a fourth mechanism, and this one reaches deeper into the brain itself. The thalamus sits near the geometric center of the brain, above the brainstem. It is the brain's primary sensory relay. Almost all sensory information arriving from the body and from the eyes and ears passes through thalamic nuclei before reaching the cortex. But the thalamus is not a passive switchboard. It actively filters and gates sensory information, modulating which signals reach conscious awareness and which are suppressed. One of the neurotransmitters central to this gating function is gamma-aminobutyric acid, GABA, the brain's primary inhibitory neurotransmitter. GABA quiets neurons by increasing chloride ion conductance through the GABA-A receptor, hyperpolarizing the cell and making it less likely to fire. Low central GABA is associated with anxiety, insomnia, pain sensitization, and thalamic hyperactivity, a state in which the thalamus fails to properly suppress irrelevant signals, flooding the cortex with noise. Benzodiazepines bind to a modulatory site on the GABA-A receptor and potentiate the chloride channel opening. They work through the same biochemical pathway that the brain uses naturally. The pharmaceutical approximates the endogenous signal. Stefan Kolsch at the Freie Universität Berlin has spent 2 decades mapping the relationship between vocal sound production, auditory processing, and limbic activity. His neuroimaging work showed that music and vocalization involving rhythm and pitch modulation reliably activate the hippocampus, amygdala, and nucleus accumbens, structures involved in memory, emotional processing, and reward, while simultaneously reducing activity in the amygdala's threat detection circuitry under conditions of pleasurable or self-produced sound. Self-produced vibration engages a different neural circuit than externally heard sound. The vibration is simultaneously produced and sensed. The larynx fires motor commands while the auditory cortex processes the return signal, and the somatosensory cortex registers the vibration spreading through the facial bones. This cross-modal activation of motor, auditory, and somatosensory cortex simultaneously is a pattern that single-channel inputs do not produce, and that correlates in imaging studies with increased GABA-mediated inhibition in auditory processing regions. Whether humming directly elevates cerebrospinal GABA levels as measured by magnetic resonance spectroscopy is not yet established with certainty. The auditory and limbic evidence is strong. The GABA connection is mechanistically coherent but awaits direct confirmation. This is how science refines itself. There is a 5th mechanism, and it is the one I find most poignant, because it involves a structure most people have never heard of. Inside your inner ear, behind the cochlea, the spiral structure responsible for hearing, sits a small sac called the saccule. The cochlea detects sound through pressure waves in fluid. The saccule was long thought to detect only gravity and linear acceleration. It is part of the vestibular system, the system that tells you which way is up. In most vertebrates, it has no auditory function at all. But in 2001, Neil Todd at the University of Manchester proposed, and subsequent experimental work elaborated, that the human saccule retains a low-frequency sensitivity extending into the acoustic range, specifically for intense, low-frequency sounds transmitted through bone conduction rather than air. The saccule in humans appears to have kept, through deep evolutionary time, a function shared with fish and amphibians, detecting vibrations carried through the body itself, not through the surrounding medium. This is not a quirk of anatomy. It is a legacy. Fish detect low-frequency vibrations through saccular otolith organs. The human saccule, sitting inside the bony labyrinth of a warm-blooded terrestrial mammal, still carries the molecular machinery for that ancient detection mode. Georg von Békésy, who received the Nobel Prize in Physiology or Medicine in 1961 for his work on the mechanics of the cochlea, documented the physics of bone conduction with precision and showed that the skull transmits low and mid frequencies most efficiently. The fundamental range of human humming, typically between 100 and 300 hertz, passes through cranial bone with relatively little attenuation. The inner ear structures receive bone-conducted sound at higher relative intensities than the same frequencies carried by air, because bone conduction bypasses the impedance transformation of the outer and middle ear entirely, delivering vibration directly to the fluid of the inner ear. When you hum, your cochlea and your saccule both receive this signal simultaneously. The cochlea processes it as pitch. The saccule, through its connection to the vestibulospinal tract and to autonomic nuclei in the brainstem, responds with postural motor modulation and autonomic output changes that are only now being quantified in human subjects. The anatomy is established. The functional implications remain at the frontier of the field. 5 simultaneous mechanisms. Nitric oxide surging through the sinuses at 15 times the baseline rate. The auricular vagal branch receiving oscillating mechanical input through the bones of the skull. The respiratory cycle lengthening into parasympathetic coherence at 0.1 hertz. Cross-modal limbic activation and GABA-mediated cortical quieting through self-produced vibration. Bone-conducted oscillation reaching a gravity sensor in the inner ear that carries the molecular legacy of an aquatic ancestor. None of these mechanisms is trivial. None requires equipment, training, expertise, or belief. All 5 begin within the first few seconds of a sustained hum. The picture that emerges is not of a single intervention targeting a single outcome. It is convergent physiology. 5 biological systems, anatomically distinct, each responding to the same physical input in ways that reinforce each other. The no-mediated pulmonary vasodilation improves oxygen delivery to the brain. Improved oxygenation supports prefrontal function and top-down emotional regulation. HRV coherence reduces cortisol release by the adrenal glands. Lower cortisol reduces hippocampal inflammation, protecting memory consolidation from the neurotoxic effects of chronic stress hormones. The vagal anti-inflammatory pathway suppresses systemic inflammatory cytokines, reducing the low-grade inflammatory load that itself drives thalamic hyperactivity and the cognitive fog associated with chronic inflammation. These effects are not parallel and independent. They feed into each other. The loop closes. Here is what I find remarkable about the nitric oxide work specifically. Weitzberg and Lundberg were not investigating a therapeutic intervention when they ran their 1999 measurements. They were trying to understand why the nose outperforms the mouth as a breathing organ, and they suspected nitric oxide played a role. The humming protocol was a methodological tool, a way to maximize sinus-to-airway gas exchange so they could measure baseline production rate more accurately. They expected to see an increase. They did not expect 15-fold. Lundberg has described that result in subsequent interviews as one of those moments where you run the measurement a second time because the first number seems wrong. It was not wrong. The paper was published in a respiratory medicine journal and attracted attention from pulmonologists. It took another decade before the cardiovascular and neurological implications were connected in the scientific literature to the same simple behavior. The science was assembled in pieces by researchers in Stockholm, Berlin, Munich, and Manchester, who did not know they were building toward the same conclusion. Now consider what you did at the beginning of this discussion. 10 seconds, 1 note, no instruction beyond sustain it. Your sinuses immediately began cycling nitric oxide into your airway at 15 times the resting rate. Your auricular vagal branch received mechanical input through the bones of your skull. Your exhalation extended, and your heart rate began, fractionally, to decelerate. Your limbic system cross-activated across auditory, motor, and somatosensory cortex simultaneously, a firing pattern your brain does not produce in response to any externally heard sound at the same pitch. And somewhere in the bone of your skull, your saccule, a gravity sensor carrying the molecular legacy of an aquatic ancestor, received a vibration that your cochlea was simultaneously processing as sound. You did not know any of this was happening. Your body did not need you to know. The machinery runs whether or not you are aware of it, whether or not you believe in it, whether or not you ever learn what a saccule is. 5 minutes of this changes your physiology in measurable ways. The nitric oxide signal is acute. It peaks during the hum and falls within seconds of stopping, because the half-life of NO in tissue is measured in seconds, but the HRV effects persist for minutes to hours after a sustained session. Vagal tone effects accumulate over days and weeks of regular practice. The limbic quieting shows up in neuroimaging as a reduction in amygdala activation that outlasts the session itself. These are not dramatic numbers. They are consistent ones. Consistency across independent measurement systems, using different instruments, different populations, and research groups who were not collaborating, is the closest thing science has to certainty about a mechanism. Hum right now if you have not already. Not because it is a practice or a technique or a ritual, because your sinuses are chambered resonators that your anatomy built precisely for this. Your brainstem has a nerve ending sitting in the skin of your outer ear, waiting for mechanical input. And your heart has been trying to find its coherence frequency since the moment you woke up this morning. The vibration was always inside you. You just had to close your mouth to hear it.